Hey, well, welcome to today's lesson. Today we're going to take a look at how we can use information about light, wavelengths and frequency of light, and how light is given off by different elements, and we can get information about how the atom itself is put together. So this is a little bit of a kind of a step into physics here, but we're going to use some funky glasses like this in class and take a look at how some different elements give off different colors of light. And again, what does that tell us about kind of where the electrons are, what's put together. By the way, man, my setup looks awesome in these glasses. I should wear these all the time, right? No, I'm going to get a headache. So anyway, back to class. So what we got today. In a previous lesson, we talked a little bit about atomic models, sort of a model about how did people in the early 1900s picture the way an atom was put together. And there was a dude named Bohr. He worked really closely with another guy named Rutherford. They worked at the same time. And they were trying to figure out more about how the atom was assembled. There was two major components to this Rutherford and Bohr model. A lot of times it's just called the Bohr model now. This little picture in the top right corner of the screen is actually an example of what that Rutherford-Bohr model looks like. It's kind of that classic picture of a 50s atom. There's a couple of main components to this particular model. Number one, there's a nucleus. There's protons densely packed up in the center. They didn't know about neutrons right at the beginning of the model, but they found out about them later. But again, they knew that there was a nucleus. And then number two, they knew that the electrons were somewhere else. The electrons were not in the nucleus. They were buzzing around at some other place. And one of these early pictures had the electrons buzzing around sort of in this particular shape. Kind of orbits that were sort of, each one had its own sort of a path around there. But they didn't really know exactly how the electrons moved or whether they were interfering with one another or if there was a bunch of them or a few of them or kind of how they all work together. But like I said, in these early ones, it's kind of this picture where each orbit was for one electron. Later on, they modified it a little bit and kind of made it look more like a solar system, like each electron was moving in this nice, neat little circle around the sun, the nucleus at the center of the atom. And in any case, this was kind of the sort of standing idea for what electrons sort of looked like, or what the model of the atom sort of looked like when Bohr and Rutherford were doing their work. And so what they were trying to do then was to kind of revise and improve upon this model to get more information about really what those electrons doing. I mean, remember, atoms are so small, we can't see them, we can't really touch them. Trying to figure out how they're put together on the inside, darn near impossible. But they were trying to figure out, again, what was going on. At the same time that Bohr was working, there was a bunch of other research going on too about light and the emission spectrum of light. And it turns out Bohr was doing an interesting bit of research onto light, and these two pieces kind of came together for him. He's thinking about the atoms in one kind of his research, and he's thinking about light emission in a different part of his research, and kind of the two of them made sense in terms of each other. So this is sort of an interesting way that the scientific process works. Bohr was working on something called electricity, called incandescence, which is this process right now. You guys know that when things get really, really hot, they will eventually start to glow, kind of like the pictures that are on the screen. Talking about glowing hot metal or the filaments in old style light bulbs. This process is called incandescence. That's why they're called incandescent light bulbs, but that's what that name of that glowing process is. And it turns out that when he was trying to kind of figure out what was happening about this, he kind of came up with this idea, not Bohr, people before him, came up with this idea called photons. This idea of little units of light, that somehow units of energy are having to be absorbed by that particular material, and then units of light are being produced by that particular material. They call it kind of the particulate idea, sorry, but they just call them photons. It's just like a little nugget of light. It's just a useful idea. When things like this are getting hot, we have to have a two-step process. Number one, there has to be energy going in, energy absorption by, say, the piece of metal. And then number two, some of that energy has to be released to us. If it was all just going in sort of an endothermic reaction, it wouldn't be releasing any. For us to be able to see it, it has to be coming out. When we take a look at these things through glasses like these, they discovered that there's a pretty full spectrum of light that's being produced by this. It's pretty much a complete rainbow. Looks just like when we put these things on in class and we're looking up at the regular light bulbs in class, where it kind of had all the different colors all blended together. This is kind of a similar idea for what we see with incandescence. This means that if a lot of different colors are being produced, that there's a lot of different wavelengths. And wavelength and energy are related to one another. So if there's a lot of different wavelengths, that means there's a lot of different types, little different quantities of energy that are being absorbed and then released. With this, we need to kind of take a look back and kind of revisit our idea about color. When we're looking at that relationship between wavelengths and energy, we need to understand that different colors of light represent different wavelengths, and different wavelengths and frequencies then represent different energies. So when we take something like a prism, or these awesome glasses, which are diffraction gratings. They do the same sort of thing. We will be using in lab smaller ones that look kind of like this, but they do the same kind of idea where you can actually split the light apart. It takes the white light and splits it apart so you can see the different colors that are present, the different wavelengths that are in there. Our eye mashes them all together, but these little guys, these little diffraction gratings with these glasses, split them apart so we can kind of analyze the different components that are there. And it turns out that violet light and red light, opposite ends of the visible spectrum, are split different amounts. The red light bends real sharp and close. The violet light bends real close. The red light kind of continues more in a straight line. So we get this sort of natural spread of the different colors. And having this prism cut at an angle like this kind of helps to exaggerate that effect so we can see it a little bit more. That's why a classic prism is always sort of a triangle shape. But there's lots of things that do this particular bit of spreading out light. Like I said, these little diffraction gratings don't look like they have little prisms in them at all, but they actually do. They're just microscopic, built into the plastic that's in there. So when we're talking about different colors of light and different wavelengths of light, this is something about these colors that are being emitted. Something else is going on. So when we have something that is incandescent and it produces pretty much all the wavelengths of light, we know that there's lots of different energies that are being produced. Bohr and his kind of group were taking a look at unique elements and heating those guys up. In this case, they didn't just heat them up, they ran electricity through them because it's much more fun. And they found out that each element produces its own unique color. Not just kind of a white light or sort of a warm red light, but some really funky different colors of light. And you can kind of see some examples on the screen here. Each element gives off its own particular kind of light. And when we look at through these, we realize that not every color of light is being produced. So there's a very limited number of wavelengths that are being produced by individual elements. Big pieces of metal or chunks of stuff like that, sort of heating it up generally, has a lot more sort of chaos to it. When we have a specific element, it's much more refined. One particular, a few small number of wavelengths are being produced. So this is something that kind of started to make him think, wait, why is it that helium is only absorbing and releasing a very small particular number of wavelengths? And why is neon so different in terms of what it's doing? Shouldn't they be the same? And so he started kind of thinking about how did this tell him something about the structure of those atoms that made up those elements. It's really cool, and this is the lab that we get to do, that we can actually make things release this energy in a more fun way by setting them on fire. My favorite. So we're going to actually take some salts, metal salts like this, and you can see sort of an example. Some of these are too dangerous for us to use, but you can see some examples that we take these different salts and burn them to get them to absorb energy that way. When they release their energy, they produce different colors. Like copper produces this really cool bluish green, lithium is like a scarlet red, sodium is a bright yellowish orange, and every one of these elements is unique in terms of the colors that it produces. Something different has to be going on with these elements that's causing them to absorb and release different chunks of light, different types of photons, if you want to think of it that way, at different wavelengths. So what we're going to take a look at is a little bit kind of a neater way to do with this. We're going to use diffraction gratings like these to take a look at that emitted light. So we want to not just look at the basic color, oh, it's pink or it's blue. We want to be able to break that light down into the individual components that are there so we can see all the individual lines, each specific wavelength. And what we'll see is kind of like the picture that's on the screen here. When you look at a helium tube, just with your just sort of regular eyeballs, it's sort of a pinkish orangish kind of color. And when you look at it through one of these guys, which is a little bit better than these glasses are cool, but it's kind of hard to tell the individual ones. When we look at through this, you can actually see a really limited number of lines, and you can kind of see a picture of what that looks like on the screen. When you look at argon through the same kind of a screen like this diffraction grating, you're going to see a variety of lines, more in the red range as opposed to the helium has a bright yellow line to it. And each element has its own sort of unique spectrum. It's not just the color that it gives off like it's orange or it's pink, but when we look at it through one of these, it's much more specific. Each one has its own sort of light fingerprint that it gives off, its unique range of wavelengths. Now, why is that? Why is it that each element has this unique set of wavelengths? Something else has to be going on. And again, this is Bohr thinking about what's happening inside the atom. Why is it that atoms can absorb and release only particular types of energies, different wavelengths, and why is it so repeatable? Like hydrogen always looks like hydrogen and helium always looks like helium. So Bohr studied hydrogen, and he was looking at this particular element. He used hydrogen because it's the simplest atom. He knew that it only had one proton and one electron, so it's the simplest possible model to work around. If we can kind of figure out what's going on with hydrogen, then we can figure out what's going on in these more complex models. He thought that that unique spectrum that's being produced by each element has to be due to something with the electrons. That's the only thing that could be moving around that's absorbing and releasing energy is electrons. Electricity is named after them, right? So we know that electrons were involved. And second of all, if those electrons are moving around in the ways that he thought at first, where they're sort of just zooming around sort of randomly or in nice neat circles, it didn't necessarily match what he was seeing with these unique patterns. So when he was going a little bit further, you had to start to kind of think about a new idea for how electrons were arranged, not just in orbits, but he started to think about the concept of something that we now know as energy levels. And this was actually his huge idea, a massive contribution to our understanding of how electrons work. Electrons aren't just buzzing around, they're actually jumping from energy level to energy level. And in order for light to be produced by an element when it's excited by electricity or by fire, there's kind of a little three-step process that has to happen here. Number one, energy has to be kind of received by that electron. And over here, it's this thing called the ground state. This ground state here, here's our nucleus is this little blue dot, and the electron is the red dot. And you can kind of picture for right now the electron sort of buzzing around in a circle. And some energy in the form of a photon, or it could be other types, but some energy is kind of zapping that poor electron. That electron was just cruising around, man. He was in the ground state. That's as low energy as he can go. And all of a sudden, bam, hit with a photon of light, hit with some energy. The second thing is, after it absorbs that energy, it's not going to stay now in its ground state. Now it's been energized, and it's actually going to jump from one energy level to a second energy level. It's going to literally bounce out into a secondary, if you want to think of it as an orbit for right now, that'll work. And it's going to bounce out and then cruise around at a high energy state, that's called an excited state for a little while. And that's after it's absorbed that energy. And then finally, it's going to get exhausted. After it's been buzzing around at that high energy state for a little while, eventually it's going to run out of extra energy. It's kind of like the electron version of energy drinks. Eventually it's going to fall back down. And it'll fall back to its original energy state. And as it falls back, it releases the energy that it had absorbed earlier. So it absorbs energy, jumps up, cruises around a little bit, and then falls back down. And in that falling down, it's going to release energy. That falling down, that release is what we then see. And that's kind of a weird idea that when electrons fall back to ground state, become unexcited, I guess, that's when we can see that energy being released by them. And that looks like light to us. So what does this look like in terms of excited electrons, in terms of energy levels? This is a similar diagram. I've just kind of rearranged it a little bit. Now you can think about this. These lines here are representing those different energy levels kind of expanding out. So this bottom line here is that ground state electron. It's kind of hanging out, low energy, just sort of chilling, doing its electron stuff. And then if it absorbs some energy, all of a sudden, bam! It's going to bump up to a higher energy state. This little wavy red light here, which has this letter h nu next to it, so there's some energy coming into it. E equals h nu is an equation that we'll see later called Planck's equation. But that means that energy is going into this thing in the form of light or heat or something, and that electron is jumping up. That's called absorption. Absorbing energy, jumping up to a higher excited state. Now at some point in time, really quickly, because it's an electron and they're traveling at the speed of light, that electron is going to fall back down. And when it falls from that excited state back to ground state, it's going to give off energy. The amount of drop is related to how much energy that it gives off, right? So if it jumps only one little energy level, a little bit of energy goes in, a little bit comes out. If it jumps up a bunch of energy, then a bunch of energy would be released, and we could see that energy coming back out, that release of energy. So again, this is that idea of jumping up from energy level and then falling back down. It has to fall back down for us to see it. Moving on, it turns out, again, back to our original idea, that energy and color are related to one another. Color is related to wavelength, and wavelength is related to frequency, and it turns out that frequency is related to energy. So they are definitely all related to one another. Here's that same equation from the previous thing. It's called Planck's equation. Don't worry about this too much. I'm not testing you on this, but this just kind of shows that energy and nu, or frequency, are related to each other. H is a number, it's a constant, so don't worry about what that value is, but those two are related to one another. So the size of the jump is related to the color that's given off. If an electron only absorbs a small amount of energy, jumps up, say, from one level to the next and comes back down, it's going to release relatively low energy light. And relatively low energy light is on the red end of the spectrum. Remember, those on the EM spectrum are the less dangerous types. As we move up to 2 energy levels or 3 energy levels, it's going to take more energy to bump it up, and it will release more energy coming back down. And the more energy that it releases, the more it's going to shift towards that blue-violet end of the spectrum, or even into the ultraviolet end of the spectrum. And that's what we're seeing over in this one, that an electron had started off in the ground state, maybe energy level number 1, jumped all the way up to 4. That's a big energy absorption. And then when it falls back down, it's going to release that same amount of energy, and that would be a blue light. So again, the difference between the amounts of energies that it's absorbing and releasing is going to relate to the color of light. Lower energy absorption and release is red. Higher energy absorption and release is towards that blue-violet end of the spectrum. So back to Bohr here and our friend. When he took a look at hydrogen and hydrogen emission, here's what it looks like down on the bottom. It's a sort of pinkish bluish sort of color when we just look at it with the naked eyeballs. But when we grab one of these guys, these little diffraction gratings, and look at it through there, or our fancy glasses like these, we can actually see the actual wavelengths of light that are being released. And it's not just pink. There is no pink there. What we actually see is this up here, this top picture. There is a red band of light, so there's some wavelengths of light that are in the red range. Then there's this kind of bright blue, and then there's some in this blue to violet sort of range. So there's actually only a couple of different colors of light that are being absorbed and released. And again, this is relating to the idea of energy levels, that those electrons have to be absorbing and releasing different amounts of energy to be able to sort of jump up to these different energy levels and then drop back down. In this case, remember, red is lower energy, and then the blue-violet is higher energy. So let's take a look at what this looks like, kind of like that previous diagram. So with this is that big idea between energy levels, that hydrogen's electrons usually start in a low energy level state, which is called ground state, and they can absorb some energy to jump up. And if it only absorbs enough energy to jump up from one energy level and then drop back down, that's relatively low energy, so that's going to be a relatively long wavelength, and we would call that red light, and that's that red picture, red line that we saw previously. The green line, or the bluish green, it kind of looks aqua on that previous page, that particular line is if it jumps up 2 energy levels and then releases 2 energy levels worth of energy, a little bit shorter wavelength, more energy, so it's in the more of the greenish blue kind of range. And then these ones that are jumping up a whole bunch of energy levels from blue, or from 1 to 4 or 5, and 1 to 6, a bunch of energy levels, it's going to drop a lot of energy, and a lot of energy correlates to that violet end of the spectrum, and we see that blue-violet sort of colors that are released there. So again, this was a huge idea, actually, that electrons aren't just flying around sort of randomly. They're sort of in these set intervals that they can jump from. They can jump from step to step to step, but they can't just sort of fly around wherever they want to. It's very particular steps that they can make, and those steps are called energy levels. Now, by the way, you may have noticed that down here it says n equals 2. N's the second energy level, and it's jumping from 2 to 3, or 2 to 4, and 2 to 5. It turns out that energy level 1, that ground state, true ground state, is so low energy that any jump up and down takes so much energy to bust it out of there that it does release that light, we just can't see it. It's releasing so much light, it's actually in the ultraviolet. It just takes a ton of energy to pop it out of that particular ground state in hydrogen. So the ones we see happen to all be from energy level number 2, just enough to be right tuned into what our eyeballs can pick up. So this is kind of a weird idea here. I know it's a lot to take in, but this is the relationship between sort of that idea of energy levels and the colors and wavelengths of light that are given off by different elements. So Bohr's work with this idea of emission spectra allowed him to kind of revisit his earlier model of the atom and to revise it to say electrons aren't just flying around in these particular orbits. Now we can say that there's energy levels and that electrons are only allowed to jump from one energy level to another energy level, not in between. So again, the earlier models, sort of random electron movement, or maybe movement in sort of these kind of weird zigzag orbits like this. As they kind of realized that there was more to it than that, when we're looking at how electrons could absorb and release energy, we started to realize that, hey, there's got to be some more organization in there. Only certain wavelengths of light are being produced, so only certain types of energy can be absorbed. So there must be something stepwise going on with these particular electrons. And that's kind of this piece right here, that when you've got certain electrons jumping from one step to the next, that's going to look like intervals of light, not just every bit of light that's being absorbed and released sort of chaotically by electrons that are in there. And then the last piece of this is that when he looked at hydrogen, he found one particular wavelength, but when he looked at other elements, each element had its own particular pattern. The emission spectrum of an element is actually a fingerprint of sorts, that every element is easy to recognize by its very unique set of colors, because each element has its own unique set of energy levels and set of electrons sort of bouncing around. Hydrogen was the easiest because it has one electron, so it's easy to trace kind of one electron moving around. If you're starting to talk about something like, I know helium's got 2 electrons, that they could be bouncing around from 1 to 2 and 2 to 3 and 3 to 4 and 1 to, and there's 2 different ones bouncing around. It gets a lot more chaotic. So it can be more difficult to see the simple patterns overlaid on top of one another when you're talking about higher energy levels. So there we go. This is kind of an overview of some ideas about emission spectrum, how they relate to energy and how energy relates to light, and then how this relates back to atomic structure. I don't expect this all to click in your head right now. We'll talk about it more in class tomorrow, and we're going to get burned stuff and wear cool glasses.